compounds. And we're going to start again today looking at coordination chemistry. So, continuing on with coordination complexes. We basically looked at these coordination complexes, and I tried to kind of tie some stuff in that introduction with what we're doing kind of with the real labs and how can we look at spectroscopy to analyze these coordination compounds. And one of the things that we definitely know and we can definitely look at, like I said, we have d electron count and relative energies. So what we can say is that the relative energies of the d orbitals on a transition metal lead to some unique physical properties including color and magnetism. And when we can look at these types of complexes historically and how the chemists of the time tried to analyze these particular compounds, color was the first thing they noticed. Even back in the 1800s, before we had any fancy instrumentation or anything like that, chemists could recognize that different colored solutions meant that something was changing. And one of the great things about transition metal chemistry and the various reactions that happen, you know if a reaction occurs because it will change color. So the color of a complex provides insight into the structure and bonding of a material or solution. And if we can some way manipulate the structure and bonding in a particular compound or complex, we can potentially be able to manipulate the color. So I introduced this unit as coordination complexes or transition metal complexes. So what we want to do is kind of define what these coordination complexes are. So a coordination compound typically consists of a complex ion and counter ions. And your complex ion is typically a transition metal with ligands coordinated to it, and the counter ion is just a charge carrier, just like it is for any of the other ionic compounds that we've observed before. So if we look at a simple salt, and one of the simplest cases here would be NaCl. NaCl is a solid, and we have sodium as a cation and chloride as an anion. They're going to charge balance each other to make the overall charge of this particular complex neutral. If we take this and dissolve it in water, we're going to get sodium plus cations plus Cl minus anions. In the case of these transition metal complexes, we can compare these simple salts to more of a complex salt. And a more complex salt would be something like this. We have CO, NH3 Cl, and then Cl2 outside these brackets. So in this case, we see roughly the same thing that we observe with NaCl, where we have a cation over here, which is this big, large transition metal complex, and we have an anion over here. They are going to charge balance to make a salt. Okay, it's the same exact concept going on here, except our cation is much, much larger. In this case, if we have Cl2, it would be analogous to something like barium chloride, which is BaCl2. So we have barium 2 plus as the cation, and here 2 chlorides being the anions to give us that extended structure. Here, our cation, what we have in brackets, must also have a +2 charge, because the chloride ions will balance out that charge. If we dissolve this in water, in solution, we're going to have CO, NH3 Cl. This is going to be a 2 plus charge. So we have this big ion in solution plus Cl minus plus Cl minus. So in terms of what we are looking at here, the complex ions that we observed in the previous experiments are what I've circled right here. In these complex ions, and typically when we look at the chemistry of these coordination complexes, we have a transition metal center, and then that transition metal center is surrounded by various ligands, which I'll abbreviate here with a capital L. They have a particular charge on them. And like I said, these are a salt, so it will dissolve in water. What the chemists kind of didn't know is how these complex ions form together. And this is a more modern day representation of how we would write these transition metal complexes. But let's kind of take a step back, and if we look through the history of how these complexes were developed, I think that gives us a good insight of where we are today and how we can understand these particular complexes, how we can understand their shapes, and then eventually we'll talk about how their color is going to be determined. So one of the things that we can say is that complex ions fascinated chemists long before the periodic table was developed due to their color. So one of the things that we need to determine is, and we can use the color of these complexes to help determine what they're going to be.